Welcome everyone to another edition of our Let's Take a Closer Look to various instruction set architectures. Instruction set architectures as per the previous videos of RISC V, MIPS, Spark, x86. Of course defining the inner workings of a processor, and similar to certainly some RISC V people said in their talks, a ISA instruction set architecture does not mean or is equal to a CPU, because that is an implementation. So one side is the specification of ARM, MIPS, RISC V, x86, and then there can be many implementations: Think, Intel Atom, Intel Core, AMD, Ryzen, and PowerPC, IBM Freescale, Spark, Sun, Fujitsu, or even this guy there, also Research, Softcore, for example. And in terms of ARM, of course, hundreds, if not thousands, of licensees. So some basics already in the previous videos. So if you're interested in all the details we discussed so far, and probably all the at least 5 or so previous videos of MIPS, RISC V, x86, PowerPC, and so on, they are somewhere on maybe this side. Anyway, so today ARM, one of the older RISC instruction set architectures, here invented in the 80s. The first working silicon working in 1985 or 6 or so, and initially built for the BBC Micro. And so Wilson developed the instruction set, writing a simulation of the processor in BBC Basic that run on a BBC Micro with a 6502 second processor. And this convinced ARM engineers they were on the right track. And then also the first working, this was back in the day, British computer manufacturer Arcan Computers. And as I said, the first working silicon, it was somewhere mentioned here, not that it mattered so much. So it is one of the earlier RISC designs. As you see here, these were the times not only Intel, x86, Motorola, 68K and 6502 and many others, Z80 and so on. And what is a little bit confusing, so similar to x86, that has a long legacy. When you look on some designs, maybe even Spark, which probably came somewhat, maybe slightly later, but definitely RISC V is how much cleaner RISC V is, and you will see this in a minute. What is also a little bit confusing is the numbering. So you see here ARM2. This even confuses me, and I work on this on a monthly basis, because the numbering is, you see here, Arcan RISC machine ARM2. Internally, this ARM2 and Advanced RISC Machines Limited ARM6. These numbers do not match the later ISA versions. You see the core licensing here. Their primary business very quickly became selling those cores, so that you or Fujitsu or even AMD or whoever, and nowadays Samsung and Apple, can implement this, unlike x86 where Intel is not really licensing that, and these cores have another version name. So although the earlier stuff, so you will see very often, especially literature and older stuff, ARM1, ARM2, ARM whatever, 5, 6, and this modern version numbers does not match. So ARM version 5, ARM version 7 are versions of this instruction set architecture as implemented in many SoCs nowadays, systems on chip. And do they have here this? Yeah, here. So here is this, and I really wonder, these are those kind of things where I wonder what the heck is wrong with these companies. You see ARM version 1, this is ARM1, okay, ARM version 2, this is ARM2 and 3, and then you see how out of sync this becomes. I really wonder why they had to do this like this. It confuses me until to this day. ARM version 3, so what this means is they, similar to Intel and MIPS and so on, they added new features and added new instructions, and increase the version. My only grief is a little bit like, yeah, seriously, did you have to do this like this? It's like, yeah, it's confusing. You see ARM 11 is ARM version 6. It's like, seriously, what the heck? You can't make this stuff up. And nowadays, of course, then they went crazy with the numbering M and A for microcontroller and application processors. And you see A17, A32, 72 is like, yeah, ARM version 7, 8. And yeah, a little bit confusing, but there we go. If we take a look, so what is different from other processors, and you've seen in previous videos that we have two classes for the most part: CISC, this complex instruction set architectures, and RISC, this reduced instruction set architectures. And ARM has this already in the name a little bit, of advanced RISC machines. And being one of the earlier RISC machines, so how does it differ to MIPS and Spark? And as I said in the previous videos, let's scroll a little bit down here. This is the usual instruction set papers. And as I said in the previous videos, so they are all completely incompatible. Although they are RISC, like PowerPC, Spark, ARM, they have all different instruction encoding, meaning these numbers used internally and all the bit fields. I'll show you this in a second. Maybe I should actually jump to that introduction to where would be a good start. This is a good start. Of course, the introduction is like, yeah, whatever, bytes and so on. We are over this already. Single instruction multiple data, our memory model, yes, bytes and words, and we got that. And 32-bit pointers, and rotate and shift and find. Come on, where would it be? So here's finally the, this is also not what memory model, floating point, instruction set, here we go. And so this is what I mean. This is why all the RISC, similar to x86, are incompatible. They all use, previous video, different encoding here. And ARM being quite different, in that we have seen in RISC V and so on, and Spark and PowerPC, they were all somewhat similar. Let's just scroll here to that. And so this is the RISC V, the modern and pretty clean. And these are the instruction encoding. So this is what your processor takes at each clock cycle and decodes for deciding what to do with it: addition, subtract, multiply, divide, load, store, and so on. And of course, they're all, again, different. And ARM being more different than the others, because if you look at PowerPC and Spark, they are relatively similar, at least somewhat. ARM is a little bit more different in that they have here, all instructions have conditional codes here in the topmost 4 bits. And this means all instructions in many ARM instructions architectures. More to this video will have 2 parts. So the second part will be the latest and greatest 64-bit edition. But so in the 32-bit, spoiler alert, in the 32-bit instruction set architecture, all instructions are conditional, meaning all, like, unlike like x86, on all the other architectures you don't have this, at least most. So PowerPC, Spark, you don't have this. You have move, subtract and stuff, and the processor is doing this. On ARM, each instruction is using this topmost 4-bit for a conditional. That is similar to on x86. You have this only with Pentium Pro. Intel added the conditional move, the C move, that if some condition is true, moves the data, otherwise not. So this can be used as an optimization for very short assignments and optimizes a jump and branch away. So this makes ARM pretty unique in that all the additions, subtractions, so you can basically each multiply in your code. So basically what that means is, let's open a terminal and favorite editor, of course. So that means all the, if you have something like if, let's say, let's hear some integer a equals, if some condition like a larger than b, that's just making some stuff up, then a divided by whatever, some divider, Otherwise, also this is a typo. This is C, by the way, C, C++, JavaScript, you name it. Otherwise, let's just say A, or it doesn't really matter much. Just something, just as an example. And in ARM assembly, this can be done conditionally, as in if greater than, like a compare, and then conditionalizing here this divide, which is something you can't do on any of the other architectures we looked at. This certainly makes the assembler quite unique, and I'm not sure if this is the best idea. It is certainly an interesting concept. However, it is constantly using and wasting the 4 bits in the encoding space. So I'm actually not sure if that is the very best idea, because looking at assembly, mostly in regular programming flow, they will be always execute. Let's take a look. Conditional fields. So that every conditional instruction contains 4-bit code field, this bits, and conditional. So here are the half multiply. What? Where would be the conditionals? Bitwise and. Anyway, there is wherever they have them somewhere, and yeah, because you certainly can use these bits for other things, for example for more registers, which is also why ARM has less registers. ARM has only 16, which of course in 1985 were quite many, given that x86 only had a handful. So 16 already better than many other CISC architectures. But RISC-V, of course, when you take a look at here, there you also see what consequences this has. These are design decisions, and this is what makes designing an instruction set architecture. Of course, you can throw some dices and do some random stuff, but that is the stuff that changes performance, and certainly something you would run simulations and do some theoretic modeling to decide what is best to spend your bits, your precious bits, as in conditional stuff, or in terms of RISC-V, 1 bit more for all the source and destination registers, because this is exactly this bits missing here for the operands, so that you only have 4 bits in ARM for only 16 registers. Other than that, you see they have here also the opcode then, similar to what we expect, like bitwise AND or subtract. These are the numbers when I simplify stuff of the processor, compares these numbers, and based on these numbers, as you see, one processor might have AND like opcode 0 for AND, and PowerPC might have 0 for add, subtract, and so on. ARM has one more unique thing. Let's see if we find this relatively fast. What do we have here? Encoding for modified immediate. Otherwise, of course, the concept is entirely the same. As you see, we have bitwise AND or exclusive or subtract, multiply. Here you see. And another thing also, apparently they have saturating add and subtract, something you do not usually find in base instruction sets. Often this is saturating adds stuff that is usually this integer stuff is overflowing. So quite some nice stuff. One thing is that many instructions, let me just try to find it here. Maybe I should look into, because what they have here is in some like operand 2, they have some scaling. It's only the question in this document where to find it. This is also something you don't find like in RISC-V, MIPS or Spark, at least not in all regular instructions, that you have some scaling. Where do we find this? Of course not. Maybe I show you when we later see this, I show you what I mean. So similar to x86, where you have some index and scale, you can have this in, now we find this. Maximum, where would be the square root? Scaling. Anyway, we will for sure soon find it. Another thing that is a little bit historically incompatible is the state of floating point stuff, that the floating point implementation was historically many incompatible floating point instructions, like version 1, 2, 3. Let's see where we find this. Maybe here. Let's see, this was virtual floating point 1, 2, and 3. If we ever find this in this document somewhere. Equation model. Let's see if we virtual floating point or vector floating point virtual. So vector floating point, they have here multiple versions which made working and targeting and implementing software for early versions of ARM always a little bit incompatible. As you see, vector floating point version 1 obsolete. Yeah, thank you very much. 20, 30 years later. Version 2, you see ARM version 5 and version 3. On most, you see implemented on most, but not all. A8 and 9, it's backward compatible, except it cannot trap floating point exceptions. And there also was advanced single instruction multiple data Neon, which of course, similar to Intel MMX and single instruction multiple data, is another optional multimedia processing engine for combined 6428-bit. And the concept, of course, the name of this instruction are always a little bit different, and of course the encoding entirely different, but this is of course in concept similar to other single instruction multiple data. So just this stuff you need for video and audio processing or 3D processing, like vectored for 3D vector, for split in 4, just what you probably have seen in the previous video. You see permitted more data types of 8, 6, 32 and so on in this 64 to 128-bit floating point registers. And yeah, encoding like this, although apparently not with this, maybe not with this conditional codes, not sure, or do they? Yeah. Another thing that ARM, not sure if they were the first, but one of the earliest, they eventually, given ARM was mostly targeting also early mobile PDAs, personal digital assistants, and later, of course, multimedia players, smartphones and or feature phones and then smartphones, and so low power devices. And what they very early did was an extension to compress, similar to what I said. The RISC always have a very regular instruction set. You see here 32-bit, similar to or identical to all the other RISC V, Spark, PowerPC, and basically all. So 32-bit regular instructions, except when you run thumb instruction set. And maybe we check with Wikipedia, was it one of the first? Let's see. Some versions support variable length instruction. That was, I'm only checking whether this was the first, maybe not. When was it even? Let's see here, that was in 1994, ARM7 TDMI. So even my first Psion Revo or 5MX, seen in previous videos, that I still have and probably should resurrect another day, this ARM7 TDMI, the T stands for thumb, and in general this abbreviation here stands for, like here, ARM version 5 TEJ, as this is thumb mode, and J is for Giselle of Direct Java bytecode, I think, execution. So TDMI is for thumb, D was probably for enhance divide and multiply or something, and whatever I was, something of that sort. You guessed it. So what is SUMP doing? SUMP is doing exactly what we have seen in RISC V. They certainly maybe took a little bit of inspiration there, because the problem with this regular RISC instructions is that they consume on average a little bit more memory than the super complex variable length encoding of x86, previous video. And where on x86 instructions can be anything from 1 byte to 15, I think. And SUMP is doing exactly something similar or identical to RISC, or similar to RISC V, in that 16-bit instructions. And what this is doing is rearranging, similar to RISC V, rearranging this encoding for the most commonly used instructions and some of the registers, so that you have 16-bit half-word instructions that consume half of the memory for better memory utilization, memory bandwidth, caching, and so on. So obviously, if your program code consumes, like, on average somewhat half the memory, then certainly twice as much fits into the instruction cache. And one thing they have done already, as I mentioned, this conditional bits, maybe not the very best choice there of encoding space. The SUMP stuff, of course, being 16-bit, one thing they got rid is the topmost conditional bits of all instructions. And let's see, where is more some instruction encoding. So quite similar to RISC V, I would say, in that yeah, you see the conditional codes are gone. Then the topmost 6 also, let's see, 6 bits are the opcode here in groups of data processing, load, and so on. And then here further putting this down, where do they have the operands? So one thing for sure, let's see, where do they have the limit of registers? So most likely in SUMP you can also, so not only all instructions, because half the instruction size, and certainly less registers. Let's see, they have a special thing of, it can be a 32-bit instruction consisting of 2 consecutive half words in that stream. And there would be the registers. I really wish they would summarize this a little bit more. Anyway, you get the idea. Probably these are all the details that would always be nice to know if you know if someone else invented this. Was ARM the very first to do something like that, or have been there before 1994, or what that was? Other compressed architectures, or well, certainly you could argue x86. But yeah, there you also see how modern, like RISC V designs, take some design cues from this kind of legacy instruction sets. One thing I would think that this instruction encoding of this conditional bits here probably makes a high-performance pipeline rather complicated, because I would think that because each instruction, so if you implement some out-of-order speculative high-performance processor like AMD Ryzen in the ARM world, I think it's probably not ideal to have this conditional execution bits here on each instruction, because in your pipeline the next instruction can always, with this conditional bits, depend on previous conditional bits set. So I would think making a very high performance implementation out of this is probably somewhat tricky for something probably not really used for that many instruction. Yeah, as you see, probably quite similar, yet some details different. And it's also interesting to see for us computer scientists taking a look at other instruction set. What have they done different in this instruction set, this conditional bits? And again, this is this kind of innovation and research you do as I mentioned in the beginning already, allocating here some bits for conditional bits or more registers. This is what you should again model and run simulations, but nowadays RISC-V certainly solves this a lot. So probably, unless you want to build some very large instruction word processor or something whatsoever, I would say anyway, stick with RISC-V these days, maybe work in this space, helps them innovate and define vector and bitmap instructions. But yeah, these are all the kind of details that you can do different and where all the processes differ. And yeah, this is that for this video. Of course, what all the processors have are different in are the special bits for like model, like processor model specific registers. For frequency settings, certainly in each SOC they are unfortunately different, and also memory management unit. You have seen the floating point, the vectored floating point stuff already, vastly different, but certainly different to PowerPC, Spark, x86, RISC-V. We have not even looked into this in RISC-V or any of the others. Is this stuff of working with virtual memory management unit, but in my opinion it's a little bit out of scope for the pure processor. And fun fact, in initial designs the memory management unit often was even a separated integrated circuit. Since the Spark Station 2 previous video, so Spark version 7 or where else? Motorola 68, 68000, 68K, as far as I remember, they probably also had a external memory management unit before they integrated that. So yeah, but these are this kind of stuff you need to know, not only the instructions and architecture to write an operating system and debugger and compiler, but for operating systems and firmware also details like memory management unit and modern systems, even I/O MMU for I/O, memory mapped I/O like PCI Express and stuff, virtualization, I/O MMU for I/O isolation and mapping, and certainly all the other bits of PCI and your device memory mapped I/O device space of previous video, 3D graphic cards and stuff. But that's a quick look for you to get an idea how the ARM instructional architecture is built and works internally. This is part 1, so I take a look at the comments and restart a new stream to have this separated for best later archived viewing, because next we will take a look at what they changed, spoiler alert, a lot for the 64-bit instruction set architecture. You might be surprised. And let's take a look at the comments. So welcome everyone. The video, Glaucus asked why is the video descriptions x86 timestamps? Because I copied this. This is stuff of you copy something on YouTube, and I can certainly delete this. Yeah, but doesn't really matter much if I delete it first or delete it later. I can also do it live. But certainly this are the stuff that YouTubers like me edit then later for all the polishing of, so they're fixed this live on YouTube. So yeah, welcome. And Navarro says ARM is still pretty good, a better choice because it's widely available, very cheap, huge quantities, recently designed an IMX8 mini embedded network Linux device. So that means you designed the hardware. That's pretty cool. Yeah, certainly. But the fun fact is it is cheap now. When before the craze of Raspberry Pi and all the cheap clones, when we wanted to do projects in 2005-6 with partners, these boards were highly expensive, right? So this is also really crazy that when you want to do a commercial embedded project back in the day, a board like an Raspberry Pi like board was like 2, if not 3, 4 or 500 euro for some low power, low performance, low power ARM device. And most of my customers did not want to pay this, right? So again, how to make a living out of open source. trying to do embedded project, and then 2005, extremely not competitive pricing. Many customers in the end often went with x86 systems because they got similar price, like think 200, 300, 400 euro, and the performance often was higher and you could run the same software. But nowadays, of course, it's changed. I remember back in the day, 2006, 7, 8, the first cheap ARM board for Linux was the Texas Instruments Beagle board. I still have an earlier version of this here. And then, of course, much later, maybe another decade later, only the Raspberry Pis. So there you see how much longer this history is. And yeah, also fun fact, I showed this already in a previous video. Probably I make dedicated videos because over the years we will certainly document a lot of stuff. Probably also make a dedicated video of my first ARM device. So in as early as 1997 or 1998, I purchased my first ARM device, the Psion Revo. In retrospect, not the best choice, but in retrospect, I should have taken a Psion 5 or 5MX, but they were just so much more expensive. But in retrospect, this extra money spent for a PCM CIA slot and more memory and so on would certainly have been money better spent. And fun fact, I've already experimentally run Linux back in that day on this Psion Westermer kind of ARM 920 or whatever that was stuff. Anyway, so that's it for part 1. We will continue also, hey, zero drop frames. A fun fact, tunnels this to the data center because drop frames, zero drop frames, but only things. I pre-tested this recurring theme of drop frames without VPN. Massive drop frames, so much too. Yeah, it's sometimes not even the DOCSIS last mile of cable coax stuff, but sometimes also congestion of peering at Vodafone, apparently peering to Google instead of running it through my own data center and peering going another route there. But anyway, if you're interested in what's changed in ARM64, see you in a couple of minutes for that. Otherwise, thanks for watching, hope you learned something, and to see you soon for the next videos and live streams to come.